Hello and welcome back to Machines, Languages and Computation. At the end of the last lecture, I presented you with a statement to do with programs and functions. And I said I wanted to try to prove that there are more functions than there are programs. So in other words, there exist things called non-computable functions. Now, what we want to do is we want to actually prove that statement. So today I'm going to have a look at what this means. So you'll remember that I told you that all computers are equivalent. That's the Church-Turing thesis. And here's that statement that I'd like to prove. It says that if P is the set of all programs that we might write on our computers, and F is the set of all functions that we might want to write a computer program to calculate for us automatically, then the size of the function set, f, which is here, and the size of the program set, p, can be compared, and we find that the function set is bigger than the program set. And that means there are some functions in here for which no program can exist. In other words, there are such things as non-computable functions. This is quite an interesting result. It's quite a complicated result as well. So we're going to take it in quite slowly over the first 5 or 6 weeks of this course. And today I want to focus on one word: proof. What does it mean to prove a statement? So a proof is a logical argument showing that some statement that we call a theorem is necessarily true. It's not the same as scientific proof. In scientific proof, we collect evidence for something being the case. And the more evidence that we find for something, the more we will believe that something is true. In mathematical proof, once a proof is written down and is found to be a correct proof, that's it. There is no argument about that statement anymore. So a statement is an expression that is either true or it's false. Here's a statement that we might want to prove to be true or false. For every integer n greater than 0, the sum of the first n positive numbers is equal to n squared. Whoa, you say, I don't understand some of that. Well, let's explain it bit by bit. An integer is a whole number. So it's all the positive numbers, 1, 2, 3, 4, 5. It also includes 0, and it also includes the negative whole numbers. But it doesn't include any numbers with a fractional component or with a decimal component. So 1.5 is not an integer. So this says for every integer n greater than 0. So what we're talking about here, we're talking about n is equal to 1, 2, 3, 4, 5, 6, and so on. What does it say? It says the sum of the first n positive odd numbers is equal to n squared. What does that mean? Okay, so the first n positive odd numbers, well, let's take an actual value of n. Let's say n is equal to 3. What's the sum of the first 3 positive odd numbers? Well, that's 1, 3, and 5. So if we add those up, we get the sum. So 1 plus 3 plus 5 is equal to 9. And what the statement says is that's equal to n squared. Well, if you remember, n was 3, n squared is 9. So what this says is the sum of the first 3 positive odd numbers, 9, is equal to 9. And that's true. But it's true for that one case. Can we prove it to be true for each and every case? In other words, n equals 1, 2, 3, 4, 5, 6, 7, and so on and so on. Can we prove it for all of the cases? Because that, it says, for every integer. Here's another statement. All even numbers greater than 2 can be expressed as the sum of two prime numbers. Again, we're going to have to do some definitions. So an even number is an integer that divides exactly by 2. So for example, 42 is an even number because if you divide it by 2, you get 21, and that's a whole number. The theorem here, or the conjecture rather, because it's not been proved, all even numbers greater than 2 can be expressed as the sum of two prime numbers. We're going to need to know what a prime number is as well. So you may think of a prime number as a number which is 2 or greater and divides only by itself and 1. 1 is not a prime number. It will never be a prime number, and I'll tell you why later in the course. But the smallest prime number is 2. Then after that we have 3, 5, 7, 11, 13, 17, 19, 23, and so on. This conjecture says all even numbers greater than 2 can be expressed as the sum of two prime numbers. So let's try it out. The first even number greater than 2 is 4. Can we express that as the sum of two prime numbers? Well, yes, we can. It's 2 plus 2. 2 is a prime number. We can use it twice. That's fine. The conjecture doesn't say that we can't do that. So 4 can be expressed as the sum of two prime numbers. One case done. What about 6? Well, that's 3 plus 3. 3 is a prime number, so therefore 6 is done. Tick. What about 8? Well, that's going to be 3 plus 5. 3 and 5 are both prime. We're done. 10. Well, that's going to be 3 plus 7. 3 and 7 are both prime. We're done. What about the next one, which is 12? Well, that's 5 plus 7, and so on and so on. Now, I've shown that this statement is true up to and including the number 12. But the statement actually says it's true for all even numbers. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and so on and so on and so on. There's an infinite number of these, and I've got to prove that it's true for all of them if I want to show that this statement is correct. So that's the challenge of proof. Now, the first of these statements, the one about adding up the odd numbers, in fact, it's true. I'm not going to keep you in suspense. It is true. It's a fairly straightforward proof by induction, and we'll prove it later on in the class. The other one, the one about the even numbers being the sum of two prime numbers, it hasn't been proven yet. It's known as Goldbach's conjecture. So if you want to read about it and the potential for proving it, you can have a read at the Wikipedia page or other sources on the internet. But we don't know at the moment. It hasn't been proven. We think it's true. The evidence points in that direction. It's been tried out for a great number of even numbers, that's for sure. But at the moment, there's no proof that it is true. So I'd like to set you a little exercise before we go into the next lecture. So before you start the next lecture, have a good think about this. Here's a statement. If A and B are both whole numbers that divide exactly by 2, in other words, A and B are both even numbers, then A plus B is also a whole number that divides exactly by 2. So what this statement is saying, being very precise about it, is that if you add up two even numbers, then you get an even number as the result. What I'd like you to do is to try to sketch out a proof of that statement, being very precise about it and making sure that your argument is watertight. You don't have to use letters, you can just use words. You can just say, oh, here is A and here is B, and do something with A and B, and therefore blah de blah. If you don't know where to start with the proof, then try this statement out for some actual cases. Take some actual even numbers for A and B and add them up. See what happens. See if you can find a case for which it isn't true. And that process might give you a clue as to where to get started with the proof.